Thank you. Thank you. Thank you. Even do you have a backup solution if movies will not work? Oh, they work. They work. They were not working on my laptop because of different contexts, but it works. So what are we doing right now will be only one talk, and the amount of material to discuss is not large, but everyone is invited to be constructively critical, because it is not just research for fun, it is an activity towards grants, and either criticism or suggestions for new ideas are appreciated. I don't know if you plan to make an introduction, but you may just give general context. Like look on David rather than me for.
I guess our goal is to model combustion reactions for some very simple molecules like methane and oxygen, or some hydrogen. So using ab initio molecular dynamics. So first, I guess I will just introduce a trick for VMD, because basically all of us are doing calculations using VASP, and in VASP we have periodic boundary conditions. So we just put Moore using VMD. We typically have this kind of bond, right? This is because the molecules are across the boundaries. So what we can do is we choose different joining method. So here we use dynamic bonds and also VDM, van der Waals interactions, I guess. So we can have this kind of image. So by using this method, we do not see the strange bonds across the boundaries. So, and this one is still have some room to improve. So we can just add the bounding box. So we can go to the console and type in some command. And so here is lattice parameters. This is angle, and this is just manually create a new box. I type in this command, we can have this black box right here.
So it just makes this cage.
Yes.
It doesn't affect the data.
No. It's just visualization.
And you need to type it. Is it possible to type it once and then just use again, or?
I guess, I'm not sure. I guess you need to do it every time when you change your molecules.
You can save a state file, like if you go to file and then down, you can save I think it's a state, and then you can just open that state later. So if you have the same movie.xyz, but it's a different configuration, and the name's the same, it will read that file and do everything that you've already done. I assume. We do that for like making MOs, because then you can just use VMD in the command line and not have the GUI open, and then you can make hundreds of images without doing anything.
I know you can save a state. I don't know.
Yeah, I would assume that the state would include this. right? Because it should keep everything that you do.
Right, if you reopen it, it keeps everything you saved, but I don't know if you can get it to read a different, like, position file.
No, yeah, you can.
Okay.
But if you, I assume that your script to make this movie.xyz just takes, like, converts your that car to this, and if you just overwrite it, it will just keep opening whatever you have. If you really want to get into how to do it, I can send you how to modify it so that you can have an argument and say, read this file.
Mm-hmm. I was kind of thinking along that line. It's like,
Yeah, so-
you should be able to tell it to, like, open a script.
Yeah, you can have it read a specific file from the state file.
Yeah, so it's like an auxiliary, and then you tell it to open
Yes.
something with the name file.
Yeah.
Okay.
So you should make a tutorial on the meeting for this.
Oh, I just have a script that says what to do.
Interesting. And I guess I should mention the cell parameters should be consistent with your postcard outcome project. So here is one model I have. This is for hydrogen. And here is the cell parameters. And we have 5 hydrogens. This is just the regular molecular dynamics at 1500 Kelvin. So
So what should we actually want to look at? Yes.
it's just hydrogen abstraction.
But is there a specific? Can you indicate maybe by finger to which part of the movie one should look? And will it be long movie or it is looped? Or it is not looped? I see.
So I guess for us, we mainly focus on the first hydrogen abstraction reaction. Because later we want to use this potential energy surface to do the quantum tunneling for hydrogens.
Mm-hmm.
So only the first hydrogen motion is important for us. And because of this first hydrogen motion, we have this kind of molecule.
And from where this hydrogen was?
It's just for hydrogen.
But from which hydrogen? So from the one on the bottom of the cell, and then it comes through the border.
Yeah, I guess so.
So this is already a relatively large cell, but maybe one can number. Does VMD allow us to label?
Not sure.
Okay, we check.
I guess for the ab initio molecular dynamics to model chemical reactions, I guess 3 factors are really important. The first one is just pressure, second is temperature, and the last is the orientation of your molecules. So here, for this one is I use TDSMD to model chemical reaction of methane and oxygens. This is a geometry optimized model. It's pretty large cell.
How do you deal with the triplet ground state?
Oxygen is always in the triplet ground state. What do you mean?
Yes, but like, what's the multiplicity of the the supercell?
Good.
Because if you have if you have two triplet, would that be a singlet, or would it be a
Multiplicity 6.
septet?
So
Right.
one, it's just add together.
So you have 1, 2, 2, 4, 6, 8, 10, 2, 4,
I have 20 oxygens.
20. So
It means
so you
40 more electrons are in the alpha configuration than beta.
I don't.
40 more configurations in alpha than beta.
Right.
It is that,
It's high multiplicity.
but is that physical?
Of course, it's physical. Why is it not only physical? Right here, we have no interactions between molecules. So every molecule is in the ground state.
I guess that looks a lot more dense than air would.
What?
The,
That's then?
the pressure looks very high.
Not really.
So you have 100. What's 12 cubed? You have around 1,700 angstroms cubed.
And I have 20 oxygen.
So PV equals NRT. I'll figure out the pressure while you talk.
So here is one trajectory from Homo minus 18 to Homo plus 8.
So what is the difference between previous one that we already watched and this one?
This one
Yes.
is just starting optimized geometry of the model.
Okay. Okay.
This is a
And
different
so what,
orientation. Yes.
I'm missing your answer to Levi's question about spin multiplicity.
Mhm.
Is it a parameter that you vary, or it is a starting configuration for all simulations? And if it is like large spin multiplicity, then Homo and Luma should have this alpha and beta indices. Is it spinless or like is it?
High sample. This is
Like I'm not criticizing, I just want some clarity.
so for this one, I just modify spin up configurations.
Okay, so it's Homo alpha minus 18
Right.
to
Right.
Luma
Uh,
alpha plus 18.
And then additionally, are you doing multi-configuration calculations? Because when
Of course not.
I assumed you weren't. For oxygen, when I was at Lano, they wanted me to look at oxygen using DFT, and it turns out that you can't use DFT on oxygen because the spin multiplicity between like the ground state and excited states are on like tens of millielectron volts. Where if you do it for DFT, it's on like 1 electron volt. How will you get around the large amount of literature that they say you should do cover cluster or CCSD calculations?
In the paper for very small systems, they can use this method. But if
I-
you're dealing
We were looking at two.
molecular dynamics,
We were looking at two oxygen molecules interacting, and that interaction needs to be done via multi-reference.
But can you do 20
Yeah.
oxygens?
Can you do Chinese for molecular dynamics?
I'm not sure. I just know that if I got a paper that had oxygen and it was dealing with DFT, a lot of flags would come up. So maybe you already have those answers to say we can deal with oxygen. But oxygen, from my experience, is a tricky molecule to do.
For me, it's just a trade-off between accuracy and efficiency.
But your results are dependent on the potential energy surface, right? So if your potential energy surface is trash, your results are meaningless, right? So if you don't get the right physics, your results are based on the physics that are incorrect.
So what? No. I'm not criticizing you because
Okay.
you are raising an important discussion. But if your criticism should be constructive, what is the measure of the right physics? Which observable should be reproduced?
I don't know. I'm asking
But
if you
from common sense, what would be your suggestion for a measure of reasonable?
So when we were starting, we were going to do machine learning potential, and we started out by looking at the interaction between two molecules, right? Because with machine learning, you can do extensibility. So if you have two molecules, then you can extend that to multiple. So when we were looking at two, the physics gave us bad trends, right?
What is hidden under the word physics?
So if we generate a potential energy surface or a scan, so like if we have them, if you have the two oxygens like this and we pull them apart, there are papers that do multi-reference, or you can do like a T or like an X, right? So if we did that scan, the potential energy surface was nothing close to what it
What was the tolerance limit like? Nothing means 10 orders of magnitude
So
different, twice different,
the
or
equilibrium,
different position of equilibrium.
the equilibrium was not bad,
Okay, that's good.
but the relative energy between the triplet, singlet, and higher triplet multiplied spin states are around like tens of millielectron volts. Well, when we did it with DFT, it was like an electron volt or 2 electron volts between the triplet and singlet,
Mhm.
which is like an order
So
to.
the role of changing electronic configuration was exaggerated in your DFT calculations.
Yes.
And you suspect that any other DFT with any other function will do the same.
Yes, and especially if you go to VASP. We were doing Gaussian, so maybe PBE and VASP, since it tends to have a smaller band gap, maybe the energies will be minimized. But with the work that we were doing, we didn't want to deal with all of this, so then we just switched up applications because we didn't want to go through several iterations of review process to say this is what we have, these are the basis for our applicability of this method to these, and then fight with the reviewers.
I guess for dissociation though, it's like
No,
the absolute energy doesn't matter.
it's not dissociating one molecule. It's the attraction of two.
Right, but I'm talking about for like something like this though. It's like the absolute energy gap.
But
For
with
men-
this, you have even more problems because now you're breaking bonds, which
Right, so it depends.
DFT isn't
like
really.
the gradient of the potential energy,
Yes.
not as much as like the absolute like energy difference.
Yes and no. So if the gradient is 10 times bigger, then you
That's
need
gonna-
10 times more energy to get it to break. So you might have to do 10,000 Kelvin, where in reality it only needs 500 Kelvin.
Right.
I'm just asking questions because I didn't know if there was a logical, like, we wanted to look at this and then you have your reasons why you can look at it.
Mhm.
Does that make sense?
Oh, yes, yes. So, what is your opinion in the following set of logical objects? Suppose you do have an applied task, applied application that needs to be solved no matter what. And then you have in your disposal like a couple of clusters, DFT and molecular mechanics.
Mm-hmm.
What would you use?
It
If
there's a trade-off between what can be done and the accuracy of that.
But if you need to have something, at least qualitative.
So I would probably do DFT.
So it is the same
Yes.
train of logic.
Yes.
Definitely, there are and there will be questions about precision, and there is a ladder to increase this precision. But by today,
It's not possible to
It's
do
not possible anything
multi-reference.
maybe like 2 years later, after a couple of clusters will be tabulated as parameters for machine learning, one can do machine learning based couplet cluster molecular dynamics.
Yes.
But not yet.
I understand why you're doing it. I just wanted to know if
If you
you're-
have
right,
some new
came
proof
over,
that DFTs
these pitfalls of DFT, or if you're just going to go and fight with the reviewers, because I don't think Sergey likes to fight with reviewers.
well, it's independent of our view.
Yes.
I guess I'm not sure about the TDSMD of this system, because from the trajectory it seems only a few molecules are really reactive.
Mhm.
Most of them just stay in their equilibrium positions. But suddenly we can have this strange hydrogen launches.
If we are going to discuss this movie, can you loop it? Let's use just exit and then enter back. There should be. So how does this TDSMD differ from thermal?
I guess maybe for this case, the orbitals are highly localized.
Uh-huh.
So when you excite between them, only atoms involved in this region are active.
Uh-huh. So thermal will not work at all?
Thermal will work.
Huh?
Thermal will, but
For
at a different temperatures, I guess, at much higher temperatures.
and here what's the initial temperature?
No temperature.
So it's 0.
Mm-hmm.
And maybe you were tracking temperature not as a figure or, but for yourself. Is there an effective temperature along the TDSMD trajectory that at which the reaction starts?
Then pay attention to it.
Just to check. It's possible to do. And what is the first reaction? hydrogen abstraction from ethane,
Yeah.
and then it's get to HO2. Is there a name for this compound? Like hypoxide?
Peroxide.
I think there's a name.
Hypoxide radical?
I honestly, I'm wanting to say some type of superoxide,
Okay.
but I'm not positive.
So peroxide is one of the 3 hydrogens.
Yeah.
So we need a name for the compound HO2.
Anti-water.
And other more reactions you see in this simulation, or it just keeps going for other methanes, forming more than one H
Di.
Hydroperoxyl.
Yeah.
hydroperoxyl. Okay, so it's more than one hydroperoxyls forming.
I remember in other trajectories there is some reaction between carbon and oxygen.
But in this one,
No, in this one.
is it only one hydroperoxyl, or
If you kind of watch the video, it seems like the hydrogen bounces around between various O2s.
so it's like proton? It's mobile hydroperoxyl.
Yeah. If you watch it, it's all the way through.
So it's proton tunneling between. Okay.
So I'm going to assume with that excitation, it excites the methane.
I don't think so.
Or maybe the bond formation energy for this fourth hydrogen is much smaller than anything else in the system, than oxygen to oxygen bond. So it's just, if energy is distributed equally, then abstraction of hydrogen will be the first reaction.
So I might have missed this. Is this going to be done in solid state or is this gaseous? Because I worked out the pressure and it's something around 10 to the 8th.
I guess should it in the middle between gas and liquid.
10 to the 8th? Pressure?
The density is definitely lower than for the solid.
Okay.
So it's pressurized supercritical gas or liquid. Practical meaning of these conditions is also debatable for applications, but from the point of view of calculations, it's the only thing that is possible based on human patience. Because otherwise, for transfer from one molecule to another, or for collisions, one would wait eternally.
Mm-hmm.
And HO2, is it number of electrons?
It's an ion.
What I'm looking at is it's a radical.
For combustion, I guess most of them should be radical chemistry. And here is just regular ab initio molecular dynamics, just signal. I change the size of the atomic model. This is raw at 2500 Kelvin. So it's a final snapshot. So interestingly, here we have this kind of molecule. It's kind of like a initial stage of polymerization. So, and I guess this kind of reaction has a special name. It's called weight growth mechanism.
Which one?
Weight growth mechanism.
Okay, wait.
So it's pretty common in combustion chemistry.
And this one is not TDSMD,
Not just regular.
it's regular. So the previous one was TDSMD and this is thermal.
For this one, I have to use a smaller cell.
Hmm?
Because in the previous cell, if I run just some MD, the temperature may be 4,000 Kelvin or 5,000 Kelvin.
How many?
5 or 4,000.
So the pressure here will be higher.
Yes.
Much higher.
Okay. Before one observes this weight growth mechanism, is there an intermediate or preliminary step of hydroperoxyl radical formation in the thermal MD?
It looks like there's a
Yeah.
hydrogen peroxide up at the
Peroxide
Ah.
or hydroperoxide?
no H2O2. At the top left front.
Okay, right.
Yeah, that one.
Okay, and other hydroperoxyls?
Yeah, it looks
I see
like
a
there's
couple
one
off
in the,
on the right.
the right middle.
Okay. So would it be possible to say that this hydroperoxyl is the first step for anything we do? Would it be okay all the time?
That, or it has to make hydrogen gas.
Why?
You need to
No,
remove.
why? How can we get hydrogen gas?
You need to remove one of the hydrogens. So it either goes to the oxygen or it makes hydrogen gas.
Okay. And it is much more energetically reasonable to go to oxygen.
Most likely, yeah.
So it will be all the time.
Typically for methane combustion, so oxygen ground state is triplet, right? So we need some heat or laser to bring it to the singulate. And then this singulate oxygen will interact with methane, because methane is also in the singulate. That's how reaction happens.
Mm-hmm.
And when both of the molecules are in the singulate, then there will be hydrogen abstraction from methane to oxygen. During this time, the oxygen-oxygen bond may break.
Mm-hmm.
So, did you ever have a chance to look at the charge on various oxygens?
Okay, I guess I can do later.
Because would the charge be state dependent? So would it change from one type of charge to another when you went from a singlet to a triplet? Sorry, from triplet to singlet?
Charge would be the same, right? It's just a radical.
Oh yeah, it just does its flow.
Yeah.
Okay, never mind.
So here are some calculations I'm going to do. So I guess I will test the methane combustion in the presence of metal blasters. This is my model, and this is just a reference point without a metal blaster.
Just thermal.
Yeah, I just want to compare how the activation energy changes.
So will the pressure between the two make a big difference?
I'm not sure about that.
So would it be feasible to like compute how much space the platinum cluster takes up, and then shrink the reference accordingly so that you don't have effects of pressure. Because if the one on the right, the pressure is much lower, then
Yeah,
it won't.
I see the point. But how can you calculate the volume of space on the cluster? Because this cluster is not stable.
It's going to degrade.
It's not degraded, but it will change its shape.
Sure. So you could do like a rough approximation, find like. So is this optimized or is this just put in?
I just created this one. No optimization.
Yeah, I don't know. Like you could take the size of this, because it's quasi-spherical, right? Or is it?
What one can do is to make the second cell smaller
Yeah.
in size, so that the density of all molecules except metal will be the same.
Yes, and that's what I asked. And then he said, how can we find the volume of the platinum?
It is possible with just high school stereometry, like compute the volume of a sphere.
Yeah,
Subtract it from
that's why I said, is it spherical? And if it's spherical or quasi-spherical, you can just take the radius, find the volume, take the difference, shave off a little bit of your box, and then your density or pressures remain the same, so that you can test it kind of more comparatively than having maybe an order or two pressure smaller. And platinum, this is ground state singlet. So you still have 20 more alpha electrons than you do beta.
Didn't check for the platinum.
What was the question?
Spin state of
Spin
platinum.
state. So I was wondering if the spin states would be the same, or do you have to add more alpha electrons for the platinum? Or would the platinum reduce the spin state?
The question is legitimate, but from the common sense, it is
Okay.
not a big sin to keep platinum fragment in a singlet.
Yes.
Because platinum is not known to be magnetic.
Yes.
If one would put like
Iron.
iron, yes, or manganese, yes, when then it would go crazy high spin multiplicity, like 50 electrons, up more than a dozen.
I think 20 electron difference is pretty dramatic.
So if hydrogen abstraction is usually the first chemical reaction, how would platinum help catalyze that? Because it'd still be dependent on the methane losing a hydrogen. And I would assume it's going to be mostly oxygen
We can
interacting with the surface.
absorb on the platinum.
The methane.
Yeah. Or they both can absorb, then the probability of them being next to each other would dramatically increase. And then it can facilitate the reaction.
Mm-hmm.
So in your experimental reference, do they have this small of cluster, or are you simulating like the step? Because in like surface chemistry, the step is a lot more reactive than the flat surface typically.
I didn't go much deeper to the literature.
Okay.
I guess there should be something.
Can you do MD with van der Waals? Or the, we,
Oh,
whatever the
This
functional is
is
called?
for DFT-D2.
Yeah, D2.
So
Would you have to,
Van der Waals is already there.
Mm-hmm.
so you are running it?
Mm-hmm. And here is just different initial configurations because previously the methane and oxygen kind of evenly distributed in the space. But here I just artificially confine the methane in this region. So I expect there will be some polymerization reactions.
Question. And it's clear that it is very much starting project. Maybe there is no answer, but from either calculation, literature, or common sense, the adsorption energy of molecule to platinum, how they compare? What is likely to in this model? Initially there are adsorbed oxygens, but there are no adsorbed methane. Is it agrees? Does it agree with common sense?
Oxidation of the metal, I guess, is just
Nature.
common sense. Yeah.
And methane is protected by hydrogens from each side, so it doesn't like to. Okay.
Actually, the carbon-hydrogen bond is quite stable. It's very stable.
Okay. And as soon, okay. But as soon as hydrogen abstracts from methane, would it land on the surface of the cluster? Would it be additional channel? So for hydrogen not migrating immediately to oxygen, but sitting on a metal.
Yeah, I guess that's the reason why the metal cluster will just increase the reactivity of the system.
If
But
it will, yes.
wouldn't the CH3 with negative charge react with the platinum versus the positive charge go to the platinum? Because platinum should be easier to become positive than it is to become negative. So why would a proton go to the surface?
Still, I guess most of them are just radical chemistry. So you have methane radical.
Yes, but Dimitri's argument was the metal cluster stabilizes the fragments. My question is, and then he said proton or the hydrogen would go to the surface. My question was, why would a positive particle adsorb or chemically bind to platinum, which is a metal, which would prefer to be positive, not be negative?
Electrostatically, proton should not sit there, but maybe there is a hybridization between S and D, things like that. And if it is just proton and generally platinum is neutral, is not overcharged, is
Okay.
negative. At least in previous simulations with platinum or hydrogen, it was big affinity for either protons.
What was your counter ion? Was it a
No
pro?
counter ion, it was charged
Oh.
and still sitting on a platinum.
Okay.
And also it's proton will be very mobile. It can sit and depart, but have some, how to say, metastable.
Hopefully, I'm not asking too many questions.
Those are reasonable. It's better you ask them. Reviewer.
Yes, because previously we have a platinum-13 hydrogen-24 model. It's quite stable.
Hydrogen gas or hydrogen atom?
Atom, but dissolved on the surface.
Okay.
Protons were covering surface of metal very densely.
And they were positive charge. Oh. Was the overall system positive? Or was it-
Originally it was neutral, and then we added more and more negative charge, and then they started slowly depart.
What was the meta cluster?
Pardon? Same.
And you put protons on, so your supercell was positive, and then you added electrons, and then they departed.
Mhm.
Okay.
Yes. Later, I will also change the composition of this cluster. And some, gold or other metals to see the reactivity. This is my last slide.
So, do you,
What's in this picture?
are you thinking about simulating a surface? So putting like crystalline platinum on the surface. Okay.
Later we will explore
Okay.
reactivity on the surface.
Which one do you expect from a chemical point of view will be more reactive?
Repeat the question.
Surface
Mm-hmm.
or cluster will be more reactive?
Clustering the reactive substantial because it surface with steps and kinks and defects is reactive, and the cluster is the one big defect.
Yes.
Can I get my pen quick?
Oh, yeah, sorry. I forgot that you teach in.
It's about 8 minutes now.
More questions to you about motivations, expected outcomes, challenges, or expected discoveries? Everyone's happy?
Would you expect CO2 as a product eventually?
If it is a complete combustion reaction and product will be hydrogen, water, and carbon dioxide. So it depends on the condition. If there is incomplete reaction, combustion,
Because ideally it should be 50-50, somewhere around
No.
1 to 1. No,
No,
maybe
you
not.
need two water for every methyl. I mean 2 oxygens for every CH4.
So 1 to 3 ratio?
1 to 2.
1 to 2, 3? Yes, 33%. So here it's like,
Here is 1 to 4. So if you let it run long enough, it should react completely and oxidize the carbon to CO2.
that's the ideal condition. That's
And
really
if you run it long enough.
not really in real world. You may have soot, right?
What was it?
Soot. SOOT.
Oh, sorry. Yes. Yes. But I assume you won't run it for more than like a few picoseconds, even if you go that far.
I guess probably for us maybe 2 or 4 is maximum.
so a best case scenario is you see that the cluster help promote those reactions?
I
Or
plan
as you
to
see them earlier?
I plan to run different temperature. I guess my guess is maybe for this one we just need 500 femtoseconds, 500 Kelvin for 1 picosecond. For this one, probably I will need 5,000 Kelvin in 1 picosecond. So
So compare activation
right.
barriers?
But shouldn't you run the exact same calculation if you want to compare? Like if you want to compare these results to that result, shouldn't you have 500?
The first step is go ahead. Okay. Semantics. You are critical to the words, not to the ideas.
Yes.
So- Thanks for accepting this. Suppose we set up absolutely ideal conditions in temperature and length of the trajectory. Second, suppose we establish success criterion as the reaction. First proton abstraction or formation of CO2, whatever, then a success will be achieved in presence of a cluster at a shorter period part of the trajectory.
Or lower temperature.
Yes.
Okay, so you
So
run.
it doesn't mean that we intentionally plan to run only shorter trajectories. It means if the trajectories are equal, the success will be achieved earlier in presence of the cluster. Does it resolve your?
Yes, but you
problem?
still do like the same temperatures.
Oh yes, yes.
You won't. Okay.
It needs shorter time
Yes.
to reach the success. While formally, conditions should be equal.
And how will you measure when things jump? Because watching videos are great. Will you use your same code that you do for like your mass spec calculation to at each time step compute each type of molecule?
We can just track the bond distance.
From what to what?
If
Like
you're interested
hydrogen,
in hydrogen
carbon?
abstraction, then you should go from carbon to oxygen, right?
Yeah, so if you measure, okay.
Would you be able to compare energies, or do they fluctuate too much to see, like if you see favorable reactions like it should, lower in total energy? I guess you could do single point calculations then, right? Once you identify like, products at some certain time step.
Yeah, and at that stage we can try different series as well. We can do NP2 as well.
Where if it's exothermic, I assume your box will heat up as the reaction goes.
Yes, and therefore it will be a chain reaction. So as soon the barrier for the first step is achieved, then there will be excess of kinetic energy that will help the rest of molecules to overcome other barriers.
So then how do you set up your initial conditions without heating to have a thermalized system? Because from Dimitri's class and what we've done, we do a heating portion which we rescale the velocities to have a specific kinetic energy. And then after that we do MD, which is Newtonian, where we don't rescale anything, and whatever as the energy goes from potential to kinetic, we get a variation in temperature. How do you set your initial conditions without that heating portion? Because if you heat it, then your reaction time scale is kind of not exactly a
Do
good.
we use the heating stage? What's the problem with the heating?
As you go, you have time for your reaction to start. So if you heat, like for these two cases, right? You want to compare them.
Okay, I've got it.
One will heat, and if you have a catalyst, then it's hard to say, oh, from our MD trajectory to when it reacted, if it's 10 femtoseconds, is it 10 femtoseconds? Or does your heating, should that also be included in your time? Because you're doing things here.
Can you do small enough steps? Or it doesn't?
Can I go this much? The waiting time in molecular dynamics is 10 to 100 times longer than the equilibration time in the heating. And whether with or without counting this time, results will not be drastically different.
So your protein is like a fraction or like an order of magnitude smaller than your 10-step in MD? Is that what you're saying?
14 times NSW for thermalization is much shorter than actual molecular dynamics.
Yes, but
And
Yeah.
you look for expectation of the temperature, it stops oscillating and equilibrates at like 40, 50 femtoseconds, and it's already steady temperature. But reactions do not start.
Okay, so it's not super reactive.
Oh, it is not. No.
Okay.
Especially this methane, I don't know if you will verbalize it clearly, but you have noticed that there were totally there were like several simulation cells, but there were two types of reactions. One is combustion of methane, and another is combustion of
The nitrogen stuff.
nitrogen 2, hydrogen 4, or whatever the
And
hydrogen.
Yeah.
So this all deals with human passions. Methane doesn't ignite. It on simulation without
You can.
without quantum tunneling, it will not ignite until substantial temperatures. You see, like 1,000.
You can open a container of methane in air and it won't explode. If you do it with hydrazine, it can ignite.
Yes.
Yes.
And it will not explode. It means if you simulate it at reasonable temperatures, there will be no reaction. So it is a challenge to get any reaction at all.
Okay.
So the question is, we are not, and I think generally the community in this area is not to the level of polishing and getting up to 7th digit. It's just to have or not to have reaction.
Okay.
So it doesn't react at all.
So for the hydrazine, is heating important at all, or is that also?
For hydrazine, all barriers are substantially lower and simulations are substantially easier. Hydrazine is less challenging because it is
More.
naturally more reactive.
So you would only really face this issue if it's like instantly spontaneous.
On simulations with
Yes.
our limitations,
Okay.
with whatever, can we do a couple of picoseconds, nothing is instantaneous and spontaneous. One needs to wait anyway.
Okay.
And hydrazine is a guinea pig to check the method, while methane is more for broader applications. More questions? Thank you, speaker, for this discussion. I want to add a little bit to the discussion on this subject and maybe on the other one, unless you are rushing to
No, you don't be Russian.
important things. So there were a presentation that most of you or all of you have already seen. So it was done half a year or less than half a year ago by undergraduate Gage Winger in the class, and there were some preliminary steps. Well, I'll skip this fun stuff. Oh, okay. So let me stop and restart and move this figure so that it will be more visible. If experimental or theoretical work is being conducted, one of the possible outcomes of the modeling would be extracting the possible pathways and writing chemical reaction that one can balance. And for combustion, it is not one. Well, simplest reaction will be just starting from these two compounds, methane and oxygen, and get into that everything will convert into water and carbon dioxide, right? So it is a reaction that can be balanced. But if one makes experiments by femtosecond monitoring of transient intermediates, or if one does the computational simulation when observes that intermediates are substantially differ from the expected outcomes from simple balancing of the reaction. So in this work by Gage Winger, there were some free source extraction of reaction pathways, and each of the line is kind of standard chemical reaction, where the final product is obtained through a chain or through several competing pathways. So if there is about 50 arrows, it means it is about 50 pathways for the reaction. So there is a possibility to get carbon dioxide, but even for the simple reactants, it is not straightforward, and one is looking forward to have this chemistry which needs. David is not here, and you got some courses in chemistry for namings.
That's methanol.
Methanol. What are the rest? Probably there are standard chemical names for all of them, right?
I don't know them.
Aldehyde.
I think that's the 1CH2O. I think that's aldehyde.
Okay. And this is a productive leg, productive pathway of the reaction that will give to generation of maximal energy, extracting all energy stored in chemical bonds and being less toxic. If reaction stops in the middle, then some of these compounds can be more dangerous than carbon dioxide for humans to inhale. And if reaction goes in the other leg, it goes to the thing that Ewan mentioned as thought or weight increase reactions. So this initial steps that were modeled and that this undergraduate Gage Winger got are like first preliminary steps, or maybe one more for hydroperoxyl radical, for methane radical, and then it has options either to go through further oxidation or for partial polymerization into this polymerized hydrocarbons, like black soot. If one puts glass above the candle, it is covered by black carbon. So it would be great to decompose the results of simulation into set of intermediates and final products, maybe in form of mass spectra on one hand, and on another as a set of reactions that connects them. So those are diagrams that Levi mentioned, and the temperature raises here just because combustion and the products are more, because reaction is exothermic. And in this simulation, it was also formation of the hydroperoxyl radical, and then there was oxidation of methane reaction path. And here the reactant were squeezed substantially, so it takes a little shorter time than nature. So in these preliminary results, there were these boxes were observed. And it is maybe if simulation goes longer or if it is photo excited, one can see either productive lack of direction or formation of broader range of hydrocarbons. So I just wonder if it would be reasonable and possible to use, maybe not necessarily this specific diagram, but diagrams of this sort as backbone of the narration to for organizing the results and telling like, okay, this simulation fits this part of direction, this fits this part, and then it will be organized tree of results, maybe. No?
You know that Dr. Hirschberger does humpback?
Yes.
Okay.
Yes.
If his laser worked,
No, if he had students.
well, that too.
No, I was just saying that because he might have some insight from experimental stuff.
Mm-hmm.
So I guess for this program, previous one, we will have different pathways. You are talking about branching ratios, right?
Mm-hmm.
For ab initio molecular dynamics, if you want to find out branching ratio, that means you should have a huge set of trajectories.
Mm-hmm.
You should have a statistical data. If you only have 10 trajectories, it doesn't make sense.
Can you, since you're already doing a method that some might not see as accurate, could you do a even less accurate, like semi-empirical calculations?
Reaction force field could be
But that
possible.
might run into issues because don't you have? Oh wait, I guess if it's designed for reactive. I know that force fields you have to do typing, and if it
The ReaxFF is designed for light molecules, and it could be a way to do.
because
The only
then
problem would be the platinum.
Yes, the platinum will be, and if you do platinum, then it will be sufficient justification of using DFT. Because definitely for platinum, nothing else can be done.
I know they have some force fields for some transition metals. I don't know about platinum yet.
I know that they have it because I'm running some force field calculations currently for
For bond breaking, for reaction,
no, for QSAR,
but not ReaxFF.
not for reaction.
Because it needs much bigger training set, so to say, to
Yes.
fit bond breaking. It is numerically challenging and to collect sufficient amount of trajectories. But if it is not a work to report but a plan, like a proposal, it can be promised, or intention to do so is nature of desire. And then it is a question of resources and amount of support. I don't know what this figure is, but I assume that for a specific reaction, it's simultaneous breaking of hydrogen to carbon bond for hydrogen abstraction, and then as soon as methyl radical is forming, it is able to play oxidation reaction with oxygen. And they are not much, in this example, not very much separated in time, and they occur in, so to say, coherent range. Those are not energies, those are interatomic distances, but for anything with, that involves hydrogen, it could be converted into quantum regime and quantum correction that can be brought in. I think it should be the same stuff. Or maybe the longer reaction. I'm just blindly showing what Gage did, and if, okay, so there is the polymerization direction, and this is CO2. So CO2 is forming.
You also have a lot of water.
Yes. And since the system is closed and energy is growing, after some regime it's not super trustable anymore, because in any natural conditions system will cool down, at least by infrared radiation, and if the system is being closed, it's come to explosion regime rather than combustion, and it can create too many radicals, which would otherwise flow away due to the pressure and cool down.
You virtually make a plasma.
It's approaching plasma from lower H. Maybe not yet, but close. Any discussion on this contribution from Gage? If no, I do have another little piece which could be interesting to. This is not announced message, and I just have added a couple of slides. So, in one of the other directions we are pursuing in research are two-dimensional materials, and the simplest one is graphene, which has I wouldn't say it is a problem, but it is the this image is wrong, but the dispersion curve, dependence of bands on momentum are very different from free space. Instead of being parabolic, like in a free space, they have conical shape, and for graphene there are 6 of them that are not in the zero momentum, but at non-zero momentum values. This is this is cool and interesting, but it is a little too quick. It is a big step for interpretation and modeling. There are materials where this conical Dirac cone appears at zero momentum, and there is only one instead of multiple. So one of this material cones for HOMO and LUMO touch each other. So one of these materials is bismuth telluride. So bismuth is trivalent, telluride is divalent. So the stoichiometry is bismuth 2, telluride 3, and it is similar to Dr. Colbert's question to David yesterday. So it is a 3-dimensional material in terms of synthesis, so it's bulk, periodic in all 3 directions. But internal structure of this material, that it is composed of layers that do not have chemical bonds between them, same as in graphite compared to graphene. So bismuth telluride, the stoichiometry is 2 to 3, and the unit cell is very small. So this colorful things are just replication. So the unit cell is about 20 angstrom high, because those are a little offset, and in X and Y direction is just like about 4 angstrom, so very thin, 20 by 4 by 4. So the HOMO and LUMO for momentum dispersion do have a cone with gap approaching zero near zero momentum, and there is a practical challenge that was revealed in previous works by Fatima, and it needs to be corrected in future works on electron dynamics with non-adiabatic relaxation. The challenge was that it's not a big science, it's just a way of organizing data, but it created a lot of discomfort and problems with interpretation. If we count electronic states just by scanning all possible values of momentum, which was just one line in one-dimensional materials, and it will be scanning like two-dimensional space in two-dimensional materials, the energies of states will be jumping up and down, and the implementation of detailed balance of the data that are not organized in ascending or descending energy is found to bring problems. So the good little technical improvement would be to arrange data, arrange the energies of states that depend on momentum in the way of ascending energy, and only then apply the non-adiabatic transitions. So if so, it is just a tip of this Dirac cone for the conduction band, and then one can just go from the bottom of the tip and then screen everything that is goes on this conical, coaxial circles. And
I might have missed the presentation. Why is detailed balance breakdown?
there are no physical reasons, but in programming, there is a trick. If you disable thermal excitations and enable only thermally activated relaxation events, then this detailed balance will be depending on comparing energies of initial and final state. And if this comparison is based on value of energy, it is additional lines of codes and additional.
So it's just implementation.
Yes.
There's no other reason why you couldn't.
No
It's
other
just
reason.
It's not implemented yet. So to do these calculations quick, you throw out what you can't do and just do what you can do.
Mm-hmm.
Okay.
But in all calculations that we did for gamma point, the orbitals were naturally ordered in ascending order. And as soon as we moved into momentum dispersion, it found to create problems here and there, and catching the bugs became a headache. So if one arranges data up front before doing any advanced calculations and just keep specific order of if the data are arranged not on the value of momentum kx and ky, but based on the ascending energy, then a lot of problems would disappear.
Okay.
Good.
Yeah, I just was like, detailed balance shouldn't fail. You just do e to the delta e divided by kt.
Yes.
Yeah.
It's not question in principle.
Yes, I
It's
got it.
question about practical convenience. And as soon as it becomes more than one index, and for all relaxation, it's like rolling ball of problems. done. It's just these little cones look like beaks of birds. Okay, are there more messages to discuss today? If no, then meeting is dismissed. Many thanks to Yvonne for sharing the data, and next time we meet in 2 weeks. Hopefully for this sequence of meetings.